Sorry, hi guys, it's Neil here again. Just want to basically make this video because I've been away from work for about a week now, and I feel I owe it to my students that I need to basically be helping them with their work. So one of the topics I'm going to look at today basically is going to be looking at models of the atom. And it's important to talk about the models of the atom because this is where fundamentally we're talking about every single object in the universe that we can see is fundamentally actually made up of tiny particles called atoms. Now, in order to understand what an atom is or the size of an atom, if you took a meter ruler and basically if you were to add little pieces of paper side by side on a meter ruler, if you were to able to like squash in as many as 1 billion pieces of paper, or even marbles, let's say, for example, if you were to miniaturize a marble, put, let's say, 1 billion marbles on a 1 meter ruler, that will basically give you an idea what the scale of an atom actually is going to be. And we're looking at a region of about 1 times 10 to the power minus 10 meters, which is basically 1 billionth of an atom. Okay, 1 billionth of a meter, sorry, apologize there. Okay, so we're looking at 1 billionth of the size of a meter ruler will give you the size of one particular atom. Now, the interesting thing is to remember is that we're not just talking about the atom, but if we were to say look more deeper within the actual atom itself, we will realize that one of the things that we need to understand, obviously at Key Stage 3 and GCSE, is that there's also more even more fundamental particles, okay, that are smaller than the size of the atom. And we're looking at the three main different types of particles we're talking about is the proton, and also the electrons, and also the neutrons as well. And these three different I normally call them animals really, because animal species of different types of particles have got their own unique properties to them. And what we need to understand, obviously, at Key Stage 3 is, first of all, we need to understand, obviously, that each of those three different particles will have a different charge. And we're talking about, for example, positive, negative, and also zero charge. And what we say is a proton will have a positive charge, electrons will have a negative charge, and neutrons will have a neutral charge. Neutral charge meaning zero. Now, as well as having charge on the protons, electrons, neutrons, remember what I said? So protons are going to be positive, electrons are going to be negative charge, and the neutrons are going to have a zero or neutral charge. Now, as well as that, we're also going to talk about the mass number, well, the mass of the three different particles, and we say that the proton is going to have a mass of 1. And the neutron is also going to have a mass of 1, but electron, what sometimes people think is electron has zero mass, but it hasn't got zero mass. There is going to be a small amount of mass, and normally in the books we have a different range of values. We're looking in the region about 1/1835 roughly. Different books have different values, but the idea is that the electron itself, electron is going to be very small in comparison to the protons and neutrons. And the thing about these particles, now that we've defined basically what the particles are, where we talked about the mass of the particle and also the charge of the particle, remembering, if you think back to what I just said, if you can remember what I said, protons have got a mass number, electrons have got a mass number, and also the neutrons have got a mass number. Remember what it was? The protons got a positive charge, and also the mass number is 1. The neutrons also got a mass of 1, but the neutrons got a charge of 0, i.e. neutral. But the electron itself is going to have a very small mass to it, like I mentioned earlier on. But the charge on a electron is going to be negative. It's a minus charge. I'm so sorry. The light on my laptop is so bright. It's actually hurting my eyes, so I'm not sure how we can actually reduce it down, but if we can, I haven't got the patience to reduce it down. I'm just going to look the other way instead. It's probably my eyes are really sensitive at the moment, and the white lights the lights are really unbearable today. Anyway, besides that, we need to understand also how the atom is made up. Well, the atom is made up of two different distinct parts to it. We're looking at the nucleus of the atom, which is going to be basically made up of the protons and neutrons, surrounded by the electron. The electron is going to be basically in a circular path, okay, surrounding the nucleus, which the nucleus is in the middle of the atom itself. And electrons themselves are actually structured in such a way that there's going to be different orbital paths, circular paths going around the nucleus. So imagine the nucleus was like this, and we have electrons basically whizzing around, going round and round and round like this, okay? Those electrons are going to be fixed within the actual electron shell. Okay, we call it electron shell because it's a circular path where basically electrons actually will be orbiting within that particular path. Okay, but the actual reason behind that is simply because electrons have a certain amount of energy in order for them to exist within the actual electron shell. Moving on slightly further on, okay, in order for the electrons then obviously to live in the next orbital electron shell, orbital path, we're talking about basically electrons actually having more energy, okay, in order for them to actually exist within a higher electron orbit. And this will continue going like this, and obviously in the sense that as electrons are basically moving in a higher or electron path that is basically or electron shells that are going to be further away from the nucleus, they require more energy. And that's really, really important, that is. So it's almost like the solar system in a way, really. For example, like the sun in the middle, the sun's going to be the nucleus, surrounded by the planets. The planets are going to be, in a rough sort of sense, the planets are going to be like electrons whizzing around. But in this case here, we also need to understand that the first electron shell that's around the nucleus will occupy a maximum of 2 electrons altogether, and that's really, really quite important that you understand that. Secondly, when you move on to the next electron shell, which will be a slightly higher orbital path around the nucleus itself, okay, that we can have a maximum of 8 electrons, okay, orbiting that path. Now, what's interesting is that when you do the experiment, let's say, for example, I'm going to move on to a slightly different topic here because I feel like it's quite important to talk about this, is that when you actually take a Bunsen burner, and let's say, for example, you get potassium, sulfur, magnesium, iron maybe, and you burn some of these chemicals on the Bunsen burner flame, what you'll find is that you'll actually produce a different color light. Now, what's interesting to note is that the whole reason why we have a different color light in the first place is because when we are actually heating up the chemicals, okay, you are actually providing energy to the electrons themselves, and those electrons are actually going to be promoted to a higher electron orbital level. And when that actually takes place, okay, from what we know so far in the laws of physics, that what goes up must come back down again. And in that sense, what happens is electrons, as they basically get populated to a high electron shell, okay, naturally they'll have to drop back down again. When they drop back down again to the original electron shell, what's going to happen is that they release energy. And when they release energy, the energy being released is going to be in the form of what we call a light particle, and this light particle is going to be called a photon. And this energy basically is going to have a certain wavelength to it. Now, we are moving on a bit more further than what I wanted to do, but in order to understand basically that when electron actually drops back down from a higher electron shell to a lower electron shell, after it's been given energy, because when it's been given energy, when the chemical's been given energy, obviously electrons get energy, and therefore they get populated to, they get promoted to a higher electron shell, okay. But as with all things, what goes up and what goes down, okay, it'll fall back down again. When it falls back down, it will experience a change in energy from a high electron shell dropping down to a lower electron shell, the original electron shell, and as a result, light will be released in a broad sort of sense, really. And that's basically what takes place here, is that when you are basically heating up elements on a Bunsen burner flame, you'll obviously you'll observe different color light, and the whole reason behind that is because electrons are basically moving from a high from moving from a high electron shell, dropping back down to a low electron shell. And that's really what we're looking at here so far. Now, if I move on forward now, basically, I want to talk about the idea for the atom now. And what happened was, originally, it was actually in Greece, and a person by the name of Democritus, okay, 460 to 370 BCE, thought that the matter was made up of tiny millions of tiny uncuttable pieces of matter. And what, in fact, the word atom comes from the word atomus, which means uncuttable. Okay, how you spell atomus is ATOMOS. So that's originally where the word came from, like in most words. Okay, Greek words. Okay, atomus. Well, in this sense here, the word came from obviously from a Greek background, atomus, and the actual model basically actually was then obviously modified again, and then we came up with the idea of plum pudding model. Now the plum pudding model, if you think now basically timescale 460 370 before Christ, okay, that's when the first original model came up with the idea of the atomus, which means uncuttable pieces of material. And then all those years later, 1897, J.J. Thomson proposed that the atom looked like a plum pudding model. And the plum pudding model, we're looking at basically something like this. If I turn the camera around here right now, you see what's going on here. Okay, if I turn the camera here right now, that's what we're looking at here right now. So we've got like a plum pudding model. Literally, basically, it will be like a plum pudding model where we got a piece of dough. The dough is going to be all positive charged. So the positive charge represents all the flour, the dough. But inside it, you are going to have electrons, charged particles, that are going to be negative or scattered around. And when when we talk about the plum pudding model, in a sense, what we're talking about really, it says here, to explain two types of to explain this atom, basically positive dough with lots of negative electrons basically stuck inside it. Obviously, what the problem with that was that this was well, one of the major not fallbacks, but major positive points with that was this was consistent with the evidence available at the time. And what we are going to mention now is that solids cannot be squashed. Therefore, the atom which makes them up must be solid throughout altogether. So, in a sense, because we can't squash the atom obviously must be made up of solid. It must be all solid throughout, and that's the whole reason why we can't squash the atom itself. That's what we thought. Also, rubbing two solids basically together often resulted in static charge. We talk about static charge now as a new topic. If you're not sure what static charge means, is that if you draw two materials together, two different materials, and you begin to start rubbing them, when you rub two materials together like this, obviously there's going to be friction. And if both my hands represented one could be like a piece of cloth. And let's say I've got a piece of cloth over here. My t-shirt will do right now. It's got incredible hook on there, by the way, as you can see right now. Okay. If I use this as one of my materials, and let's say I had something plastic, I've got my can't go wrong with that protein. Okay. Well, it's got squash in there really, but here we go. We got a duster. And we got a piece of plastic. Now I'll start rubbing it like this. Now what's really taking place on an atomic level is that electrons basically from this piece of cloth will be basically removed and actually added onto the plastic material here. Now when that takes place, what's going to happen now is there's going to be an imbalance of charge. When I mean by imbalance of charge, that means some of the electrons from the cloth will actually be removed. Therefore, what happens is that the net charge, the overall charge on the piece of cloth will now become positive charge. And the reason why it's positive charge is because if you've got an equal number of electrons, an equal number of electrons, and equal number of positive charges, and let's say 3 of the electrons basically got removed, what happens now is that the positive charges obviously dominate. And what I mean by dominate is more positive charges compared to the electrons here. As a result, the overall charge will become positive. And that's essentially what we're talking about here. So this material here will become positively charged, but at the same time also, electrons basically add onto here. There'll be more electrons here compared to the positive charges, making this more negative. And that's basically the idea of static charge. Right, next lesson, I'll be talking about basically the next version up, the improved version of what the atom, what generally how we basically perceive the atom now, and that was obviously many years later, and that is going to be a major topic for our next session. Thanks.